the topic of restriction bounds and how it relates to nodal sets has been a lot of work done on that recently. So I'm going to focus on some very specific things that I've been involved with and interest me probably the most. So before I start, let me just sort of tell you the basic problem that I got us interested in restriction bounds and connection nodal sets. So there's a paper by Zeldich and myself in about 2009 where we considered the following problem. So you take an analytic domain. It could be piecewise analytic, but let's suppose it's analytic. Okay. So here's my omega. So the boundary's piecewise analytic. And so we, again, so let's consider, for simplicity, the eigenfunction problem with Neumann boundary conditions. You can do Dirichlet, but it's easier to talk about Neumann. And so we considered the zero sets, right? And in particular, we were interested in determining how many of these components of the nodal set intersect the boundary, right? So we looked at the following. So here's some nodal. Here's a nodal. Is a component of the nodal domain. It could be long, right? So we considered the following problem. And what we did was we proved. So the boundary here is C omega. And what we proved was that this was O of lambda. Okay, so my eigenvalues are going to be lambda squared, so lambda is the square root of the Laplace eigenvalue. And the O, of course, depends on the boundary. Depends on the
Is R2 or in
R2.
Oh.
This is in R2, yeah. For the planar domains.
Basically, just counting zeros.
Yeah, exactly. Yeah. Yeah, exactly. So, and so we prove this at the boundary, and then the natural question is sort of what happens if you.
Counting zeros, but it's sharp. That's what's interesting.
It is sharp, yeah.
Sharp.
Yeah, yeah,
Unusual to get sharp.
yeah, yeah. So it's exactly like nodal length. It's that scale, which is what you expect. We also asked the question of how many how many of these things were short on the order of the fundamental frequency and how many were long that went across like that, but we have no, to this date, we have no way of estimating these things well. So, but the natural question is, so suppose you, instead of looking at the boundary, you looked at some curve in the interior, right? Right? And you ask the same question, right? So now H is C omega. Analyticity is crucial for this. And you ask the same question. So you nodal set. I mean, obviously this could be infinity, but if it's infinity, it's infinity, right? So the question is, can you estimate this? What is when do you get the O of lambda bound here, which depends on H, right? So at the boundary, this is automatic. And that basically follows by Karleman. It's unique continuation. At the boundary, you have boundary conditions, so that it's the same thing as Karleman. You can show that the crucial point is here that at the boundary, if you compute the restricted L2 mass on the boundary, it satisfies a unique continuation estimate like that. That just follows from interior unique continuation and potential layers, right? But if you look at this problem, we're faced with exactly the same condition to prove a theorem like this. The reason is it's a Jensen type argument, and you have to normalize the mass. So the question is, so the key estimate to proving something like this is a unique continuation estimate, but the level of curves, right? So the key estimate that one has to prove is right. And so the question is, this suffices, yeah.
Why does it suffice?
Because the method involves.
No, but I mean, I take a curve, a piece of curve for which the estimate holds. consider all those eigenfunctions and start doing wiggles for the rest.
I don't.
So that estimate is monotone in H. But I
H is
but
fixed.
H is fixed.
H is fixed, but I fix half of it for which it is true, that estimate.
How do you know?
There's few intersections, but then I create a band curve for which you have plenty intersections.
It's not monotonic.
What is not monotonic?
There is no box in principle.
No. If I want to get the curve, if I want to get the curve, I have a better estimate here, right? If I have it for a part of H, I have it for H.
Yeah, but
And
how
I
do
can
you?
create a
But how do you know you have it?
wiggly
How do you
part
know
of
you
H.
have it for part of H?
You cannot have it for a part of H. it has
No.
to be for-
The function may be very tiny.
Function is very no.
The phi, the restriction.
Yeah,
So
it's
so
a-
it claims that there
And the
is no
derivatives, okay.
that there is no closed curve for which is estimate for points, and that somehow
That's the question.
That's the question. Yeah. So, the reason is it's a Jensen argument. What we do is we take the restriction of the eigenfunction to H. That's real analytic. Holomorphically continue over H and count complexity.
H is real analytic.
Real analytic.
Oh,
yeah.
okay. You said C.
C omega.
Omega is real analytic.
No, it has to be a real analytic. Yeah.
Okay.
Yeah. So we count complex zeros. So it's a Jensen argument. So you need some way of knowing.
Pedro, this could be the zero set of the eigenfunction.
Yeah, absolutely.
You
Yeah.
know, this could be part of the nodal domain.
Yeah.
so
You could have infinitely many of these things a priori.
No, I missed real analyticity actually. I see.
Yeah.
Yeah,
Yeah.
okay.
So this is where, for me, restriction bounds first sort of entered into the picture, right? So this is for upper bounds of nodal counting. They also appear for lower bounds, but that's sort of a different talk. I think Zeldish will probably talk about that tomorrow. So I want to focus on upper bounds for these counts. These have lots of applications, but so I want to talk mainly about restriction bounds, and then I want to give some applications to nodals to this problem. Okay. So one wants to characterize classes of H's for which you have estimates like this, right? So okay, so let me just begin with some sort of basic stuff. So suppose omega is a strictly convex, smooth, bounded planar domain. Now omega is different than the omega here. Omega just bounds. Suppose I have some curve. Okay. This could be in a manifold without boundary or with boundary, it doesn't matter. And so omega will be the interior of this thing. It bounds some domain. And so let's suppose it's strictly convex for simplicity. So I can talk about the billiard mapping. Right.
Right, there's omega and H. Are you now restricting to the inside of H, or is this?
Yeah, it's inside of H. It's a different omega.
That's good.
Okay, it's not that omega. No, omega, yeah, I know, sorry. Let me call it omega sub H, okay?
Okay.
It's a different omega than the omega there. Okay, so it's just H is just the boundary of some domain omega, so let me rub this out so there's no confusion. Okay. Okay. And so you can consider the billiard dynamics, right? So you basically take a point in the interior cosphere over H. So it's a vector unit length that points into the interior, and you go here, and then you reflect using equal angles, and then you continue, and that determines the billiard dynamics for such a domain, right? And so there's a cross-sectional flow, which is exactly the billiard flow. So you give yourself an initial direction, unit length direction at the boundary, and you can consider the dynamical system given by the billiard flow.
So what do we do? The next intersection?
Yeah, next intersection, then you reflect by equal angles. So it's a Snell law, right? And then you keep doing this, right?
So Q is the point, and beta is the
Q is the point on the boundary, yeah. So Q here is the point on the boundary, and what is it? Eta is this unit length vector, right?
Yeah, you map to the next.
You map to the next, yeah. And you keep going. Now, you can project this onto the tangent space of H, so you can talk about vectors in the ball bundle of the tangent space. It's the same thing because you just take a projection onto the boundary. So that way you get a dynamical system defined. Where am I here? Okay, here. You get a dynamic. If you use stereographic projection, like in the picture, you have a dynamical system that's defined on the cobalt bundle of H, which I view here as the boundary of this domain. Okay. And so you have this billiard map beta. This is the billiard map on the cobalt bundle. Okay, so this is just sort of a basic business, but so this preserves the symplectic form. So there's a real dynamical system here. So if I take just the standard Liouville measure on the boundary, then this beta preserves the symplectic form. So this is an old result of Birkhoff, going back to the 20s, I believe. And there's your billiard map. Oops, right here. Okay, so I just wanted to point that out because that's going to be related to the question I want to talk about as far as restriction bounds go. So, okay, so let's take a compact closed manifold with Laplacian. What I'm going to say is it can be generalized to all kinds of operators, but I'm mainly interested in this, so let's just talk about that. Okay, and so you take a usual L2 basis of eigenfunctions. My eigenvalues are lambda squared, so keep that in mind. There's always a square issue. And I'm going to take H as an orientable smooth hypersurface. For most purposes, I'm going to assume it's separating, so basically it bounds something, okay? And so then the question is, I want to estimate the L2 restrictions. What I'm going to talk about are basically, are mainly lower bounds today. So there's a whole question of upper bounds, but lower bounds are interesting just from the point of view of the question that I...
Small means C infinity or...
Huh?
Smooth means C infinity.
C infinity, yeah. You don't quite need C infinity. C2 will do for most of what I say. So I want to estimate the restrictions basically from below for the obvious reason that I started with, right?
But that reason works on the quantum.
Mm-hmm.
That reason works on the quantum.
I know. I'm going to ask this in general for smooth, and then we'll talk about it. If I can prove it for smooth, all the better. But
Yeah.
Okay, so what's the reasoning? Well, I like to do L infinity results, but they're very hard. There are very few, they're results of Ivan and Sarnak that give polynomial improvements. In the arithmetic case, there's some improvements in the integrable case. You can prove Hardy for example, Liouville metrics on tori and things like that, but very few polynomial improvements known. And even for negatively curved surfaces of variable curvature, you have sort of a log improvement, which is kind of, we've been stuck with that since the 1970s. So it's difficult. So, I mean, to be honest, restriction bounds are somewhat simpler because you are integrating. But more importantly, our points 2 and 3. We're interested in the problem of quantum ergodicity and how it relates to restrictions to hypersurface. So quantum ergodicity, I'll say more about it in a minute. But basically, it says that if you have a manifold with an ergodic geodesic flow, then for most eigenfunctions, they're equidistributed, okay, in a certain sense that I'll explain. And so what we asked with Zelda several years ago was, well, how robust is that? Can we talk about equidistribution when it comes to hypersurfaces? So that's sort of a natural question that is obviously related to restriction bounds. And 3, which is the thing that is probably most interesting for this talk, is this thing that I just talked about, namely they're very important in the study of eigenfunction, nodal, and critical sets, both for upper and lower bounds. Okay, I'm going to talk about upper bounds, but they're also important for lower bounds. Okay, so let me start with some general results. So for Laplace eigenfunctions, there are universal results of Berkshire-Zvetkov. I proved upper bounds for LP restrictions, all P, all dimensions. I'm going to focus here just for simplicity on dimension 2 and P2. I'll be talking about L2 restrictions. So in the case of L2 restrictions, there's a universal upper bound that's like this. And so it's the square root of lambda. So if the eigenvalue of the Laplacian is lambda squared, this is the 4th power. So the quarter power of lambda. of the eigenvalue of the Laplacian.
So it follows from an infinity is to be.
Hmm?
It follows from an
No,
infinity.
the infinity is the worst exponent.
That's the worst exponent. L infinity is you square that. It's lambda.
It's a much stronger.
Yeah. So you see this.
Sharp on a sphere.
Yeah. So if you look at this example of the sphere, you take the zonal harmonic, not the zonal, the highest weight harmonic on the sphere, right? If you L2 normalize it, this one that I'm talking about, so this is a function of x, y, z. It's some constant, which is irrelevant. And basically a quarter power of n. So the eigenvalues in the case of the sphere are n times n plus 1, right? So it's basically like n squared. So if I L2 normalize this eigenfunction correctly, I take the quarter power, and then I take x plus iy to the nth power. This is obviously harmonic, and it gives you the spherical harmonic. And when, since the, on the sphere x squared plus z squared plus y squared plus z squared equals 1, when z is different from 0, the modulus of this vector is less than 1. So this decays exponentially off the weight here. And if you just compute the L2, it's obvious that you get exactly this bound. So it's saturated. So this is sharp. When you have positive geodesic curvature, so if instead of a geodesic you talk about a caustic or something like that, so if you take something like here, if you talk about a curve with a positive geodesic curvature, then you can improve the estimate to 1/3, and that's because of the area estimates. I mean, so I should say that Hassel and Tacey generalized these LP bounds to semi-classical case. And all right, so there are large improvements, first of all, in the case of flat tori. So there, in the case of flat tori, at least in dimension 2 and 3, Bourgain and Rudnick can prove, basically the best possible estimates you can hope for, if H is positively curved. So you need a curvature assumption there, which actually will come into what I'm going to talk about later too. But so if this is for tori in dimension 2 and 3, this is tori, and this is Bourgain Rudnick. In the case of arithmetic surfaces, there are also large polynomial improvements in restriction bounds. So, for example, for horocycles, one has bounds that are very close to this. You have lambda the epsilon or lambda the minus epsilon, I think, due to Gauch-Reznikov and Sarnak. There are some additional improvements in certain quantum completely integrable cases. And recently, Blair and Sogg proved log improvements in the negatively curved case. So log improvements over the universal bounds. But, again, not that much known. So these are upper bounds. So we want to mainly talk about lower bounds. But so let me return this. Let me sort of define what I mean by quantum ergodicity. So I say a sequence of L2 normalized eigenfunctions is quantum ergodic. I'll call that QE. If you take any symbol, any function, if you want, you could take it a function on the base if you want. And if you take the matrix values of the eigenfunctions relative to this function, it's equidistributed, right? So basically it tells you
What is the base and whatever?
A is a function.
Where?
It's on the function. It's a function on the cotangent bundle of the manifold, but you can take it to be just a function on the manifold, okay?
Okay, can you function of the way?
Yeah, it's more general than that, but you take.
What is open way?
It's kind of, if you just stick to the manifold, you get.
It's just multiplication. Okay, think about this.
You lose the dynamics, that's extremely important.
Yeah, it is, but okay. So
Dynamics and configurations.
in the case of functions, okay, all this says is the following. So it's much more general than that, but in the case of functions, so if A is a smooth function, okay, then what this says is that if you integrate A against the absolute value phi a, then this is the integral of a with respect to the volume measure up to some.
So pi lambda squared. That's
Yeah, you can. This is equidistributed. Okay, that's what it means. As lambda goes to infinity. It's more general than that. Op is a differential operator that you quantize as that function. But if it's a multiplication operator, it's just that. So it just tells you that there's equidistribution of eigenfunctions in phase space. So that's a particular example. So the basic theorem here is exactly what I said a few minutes ago, that if you have a compact closed manifold with ergodic geodesic flow, so a hyperbolic surface, for example, and d mu is Liouville measure, so it's induced from Riemann measure on the cotangent bundle, then there exists a density 1 subsequence of eigenfunctions. That means that for most eigenfunctions, there could be thin subsequences that do not satisfy this. But for most eigenfunctions, you have equidistribution. So this is theorem of Schnillmann, Zeldich, and Collin de Verdier. So here's a particular example of an ergodic system. By the way, I stated it for manifolds without boundary, but for manifolds with boundary, it's also true. So that was proved by Jardin-Lechnam for certain cases, and then it was generalized to arbitrary smooth manifolds with boundary by Zaworski and Zeldich. Somewhat later, late 90s. So it's true on manifolds with boundaries. So this is the case of the stadium, and you look at a particular eigenfunction plot, and so the point is that one would expect that most of these eigenfunctions, most of these eigenfunctions are equidistributed in that sense. Okay, so as I said, the question that we dealt with, that we got interested in, was how robust this quantum ergodicity result is when one looks at hypersurfaces. So we're going to look at restriction bounds to hypersurfaces. So gamma h here is just the restriction. It's just a restriction to. It's just a restriction to a hypersurface. It's just a restriction map. So we do the same thing. We look at matrix values of restricted eigenfunctions. In this case, H is some hypersurface. There's some asymmetry condition with respect to the geodesic flow. So the asymmetry condition means the following. So if you have a hypersurface, right, you consider directions like this, psi, and then you look at reflected directions, let's say RH of psi, reflected in the hypersurface. And so this comes, and after a certain time, it hits the hypersurface, and at a certain time, this comes and hits the hypersurface. If these angles, so you want to look at the vectors for which these angles are different. Okay, so there's no perfect focusing. So the measure of the measure of the size for which you have perfect focusing in this sense is 0. Okay, so that's what asymmetry means. That's okay. So if you have a hypersurface that's a fixed point set of an isometry, then of course everything is reflected. So the measure is 1. So you want to rule out cases like that, right? So this notion of perfect focusing has to be measure 0. Okay, that's what it means in practice.
After any time, right? So
Yep, at the same time.
No, I understand, but the time is not.
For any time, but the same time with the reflected.
That's like if Ree's condition
Yeah.
in the variable.
Yeah, it's instead of looping, here you have your hypersurface, it's a focusing condition, a defocusing condition. Okay? Because it's not true otherwise. I mean, if you have a fixed point set of an isometry, you look at the odd eigenfunctions are identically 0.
Yeah.
So you have to rule that out. Okay? But otherwise, again, you have a density 1 subset. So for most eigenfunctions, if you have ergodic geodesic flow, then they're equidistributed. So in this sense, exactly the same thing holds for at the level of restriction. So it's quite robust. Unfortunately, we don't know that this density 1 subset is the same as the density 1 subset in quantum ergodicity. There's no way that we don't know how to prove this. It may not be, for all we know. Yeah.
So beautiful functions squared and
Yeah,
multiplied
so,
by something.
yeah,
It's
yeah.
not reasonable,
Yeah, exactly. But now at the level of hypersurfaces.
yeah, depending on so
Yeah, yeah. Okay, so, but you have this price you must
I
pay.
think one should emphasize here that when you restrict to a hypersurface, even the fact that the L2 restriction norm should be uniformly bounded, that's certainly not true. So
Right.
but on the subsequence, it is true. That's
Yeah. Yeah, absolutely.
If you normalize the L2 norm could be 1 on the whole space.
Yeah.
And that's
okay.
Yeah, so a priori you could have thin subsequences. They do. They can blow up, right? So
Yeah,
you could, yeah. All right. So, but there is this price that you cannot directly relate this result to the quantum ergodic eigenfunctions because you run a variance argument. You have to throw away thin subsequences that might differ from the ones you throw away for QE. Okay, but so let me just say that this result does apply to things like geodesic circles, closed Horus cycles, generic closed geodesics, not this kind, obviously. These ones are ruled out. If it's a fixed point set of an isometry, it's nonsense because half of them are 0. But for most geodesics, it's true. And then these results have also been extended by Dyatlov and Zworsky to Schrödinger operators and arbitrary manifolds with boundary. So we proved it with Zeldich for Euclidean domains with boundary, and then for manifolds without boundary, and they extended it to manifolds with boundary. Oops. So this point is just the point that I was making a minute ago, that the density 1 subsequence that you have to throw away might not agree with the sequence of QE eigenfunctions on the ambient manifold. That's a big problem.
Why do you care about this takes intersection?
Sorry?
Why do you care? Why do you worry?
Well, because if you then have a theorem that says you have all eigenfunctions are quantum ergodic, like Lindenstrass's theorem, if this were the same sequence, then you would.
But this is in a very special situation, all of them.
Sure. But we'll talk about general cases, but
Yeah.
this was sort of a,
I wouldn't worry.
yeah.
Exactly.
Now I wanted to prove some results for the stadium, right? So that's what I'll talk about in a little bit. So okay. A basic open question here is given an equidistributed sequence on the ambient manifold, under what conditions on the manifold, the hypersurface, and the dynamic symmetric do you have to put so that the restrictions are actually satisfy quantum ergodic restriction, so that they're equidistributed along H. So one way to link these problems, to link the problem of equidistribution on the ambient manifold and equidistribution along the hypersurface, is to consider a slightly different setup. So again, I consider some sort of eigenfunction problem, and so we have standard eigenvalue problems. So one can consider, instead of just the restrictions to the hypersurface, you can consider the Cauchy data, which involves 2 sets of data, right? The restriction and then the restriction of the normalized normal derivative. Whenever I take normal derivative, I multiply by h. H here is 1 over lambda. So whenever you differentiate, you have to maintain the order 0, so you multiply by h. H is 1 over lambda. Okay. So that's the Neumann data that you look at. So the normal derivative is the Neumann data. The other one is the Dirichlet data. And so you can try and prove quantum ergodic restriction theorem involving both sets of data, right? And so that's what we did a little bit later with Christiansen, Zeldich, myself. So we considered a smooth embedded orientable separating hypersurface. So this just means that the hypersurface bounds something, right? Okay.
Just to answer Misha's question, I mean, there are situations, very rare, that we know that you have a the whole space, and we now want to use that.
Yeah, exactly.
That's why.
But because we are sure that these situations are very rare, so they're very special, right?
That are proved, yeah. But there's no theorem about quantum unique ergodicity for restriction in
No,
any case.
not in any case, no.
Not one case, no.
Not one case. For the reason I mentioned, is that you don't have. So here you pay a price. The price is a heavy price because you now have to include both sets of data. But you can link the equidistribution theorem you have along H directly to QE sequences. So this is important, right? So here, if you take any interior QE sequence, so it's an interior sequence that is equidistributed,
The second interior means on the entire manifold?
hypersurface again.
Or on the hypersurface?
You take a QE sequence on the interior on the whole manifold M. So M is the whole manifold. H is your hypersurface here, right? So you assume that the eigenfunction sequence is equidistributed on the whole manifold.
So the condition on M is a very soft condition. It's just the integral against volume. But now I want to get something much stronger.
Now I want to get something along H, but I get it for the Cauchy data for the normal derivative and oops, I keep pressing the wrong thing. The normal derivative and the Dirichlet data, and what you get is it looks almost like what you would expect. It looks almost like a sum of squares of Neumann data and Dirichlet data, and this is just some volume. Okay, so this is what you want. The key point here is that there is this tempering factor here, which is the identity plus h bar squared. What is that? What is that letter? delta sub h is a Laplacian along h. So this thing tempers the growth of the Dirichlet data along h. That's crucial. If you leave that out, it's false, right? So this vanishes. The symbol of this operator vanishes exactly in the tangential directions to h. So that is sort of the one feature that that is not sort of completely straightforward, right? Is that you have to temper the Dirichlet data by something that vanishes. The symbol vanishes in the tangential direction because the Dirichlet data a priori could blow up. So this tempers it. The Neumann data never blows up. Okay, so we proved that with Hassel, Christensen, and myself, and then Melissa gave a different proof a bit later. So if you look at the Neumann data, it's different than Dirichlet. So this is true for any hypersurface, any dynamics, nothing to do with dynamics. If you take the normal derivative, okay, the capital D just means you put a 1 over I, and I don't care, okay? You take the normal derivative of this, you multiply by 1 over the eigenvalue, this is all 1. For any h, anytime, anywhere, okay? So this first term is bounded always, right? The only way this is bounded, but you have to put in this tempering factor. But you have this sort of quantum ergodicity result at the level of restrictions, but for the Cauchy data. The nice thing is that it relates it directly to whatever eigenfunctions are equidistributed on the ambient manifold. Okay.
So now there are no restrictions on H? Or?
Sorry?
There are no restrictions.
Just smooth
Yeah,
overhangs. Yeah,
understand,
that's
but
all.
nothing like that.
Nothing like that. No, just smooth. There's no restriction on H. Just smooth. The price you pay is you have to. Damn it. The price you pay is you have to include both the normal derivatives and the function restrictions. Okay. Otherwise, no restrictions. Okay. So yeah, I just wanted to. So this result holds for all.
And one stupid thing, why doesn't the first term blow up?
The first term.
So,
Yeah. Well, so we prove.
Second one.
Yeah. Why? So this. Okay. So I don't have a quick answer to that. Probably the easiest. Well, yeah.
Because what I'm thinking of is that if
It's a flux
phi
term.
blows up beyond what it should be, then
Yeah. Well,
there is
don't.
a
Yeah, but
descent
don't
with-
forget you're multiplying every time you differentiate. You have to multiply
Yeah,
by
but
something
there
to
is
temper
descent
it.
within like H.
Yeah.
So
Yeah.
the normalization actually is just normalization to the
Yeah.
same amount.
Phi to blow up, it has to be localized so it isn't oscillating in the normal direction.
Yeah. You see, that's the point. Is that yeah, exactly, right?
So phi might blow up, but if you apply a derivative in the normal
It kills the tangential part actually.
So you should think of the example that he has concentrating on.
I'm thinking that the total gradient is huge. Right?
Hmm?
If phi blows up, the total gradient is huge. Because within H distance you have 0.
No, sorry, I don't understand.
The total gradient.
the
total
total.
gradient is at least as large as 5 if you multiply it by H, right? Somewhere nearby within
Any,
H
a derivative in
distance.
any direction, yes.
Yes.
but
Yeah, but the normal derivative is.
happens in the tangential
Yeah,
distance.
no, yeah. The tangential direction is the bad one. That's the one that.
So the zeros are just
Yeah.
the nodal
Yeah.
domain somehow in that case accumulate across the surface.
Yeah.
Why? The surface is just anything, right? It's a little bit surprising. Okay.
It's true. Yeah. I mean, the easiest way to see this is if you write down potential formulas, right? I don't want, yeah. We'll talk.
I mean, H doesn't know about the eigenfunctions. H can go directly.
No, it doesn't know about that, no. It's any H.
That's my
Yeah.
problem with
Yeah,
it. So
yeah,
my
yeah.
idea was
But the normal derivative does know about H. So it's a particular
the
direction.
normal derivative does know about H, but
Yeah.
it's pretty much the same as the whole gradient unless you
No,
verify
it's very different than the tangential derivative. Yeah, very different.
So these,
for phi, an eigenfunction. How does it know about H? That's what
these
No,
are
th-
eigenfunctions which may restrict onto H, have large L restricted L2.
Yeah.
That's the power of
Exactly,
the
exactly.
function.
That's the problem. Phi has a huge L2 norm restricted
Yeah,
to
but
H.
then in the tangential derivative, normalized this way, it's not blowing it.
Okay.
Yeah.
So the conditions that the L2 norm is large somehow makes normal derivative. Okay, maybe.
Yeah, it kills
If you
the.
just write down
Surprise.
this harmonic you wrote down there, you see everything.
Yeah. Yeah. You write down. Yeah. That exactly that question. That example. So, okay. So the main question is, I mean, I want to return to this question of L2 restriction bounds for the actual eigenfunctions, right? So the main problem is how do you separate out restriction bounds from Neumann data from Dirichlet data in this formula that I just wrote down, this thing here, right? So that's sort of the basic issue with this, right? If you want to actually talk about Dirichlet data. So so this theorem that I just wrote down relates Cauchy data to the intrinsic billiard mapping. Okay, I'll say something about that in a minute. But I just wanted to say that this term here, this thing that I multiply by this operator, this is elliptic off the tangential set. So this is perfectly nice off the boundary of the Cobol bundle, which is the cosphere bundle. This is the tangential set. So this just picks out all the tangential covectors to H. And what you can see from this is that if you look at this estimate, and you sort of break up into tangential part and non-tangential part, when this is non-tangential, if you look at the non-tangential part, this is elliptic, so this just behaves like the L2 restriction, right? This is O of 1, so it doesn't matter, this is O of 1. So everything is controlled. All the mass is controlled by, up to O of 1 errors, is controlled by the tangential mass. So if you look at the L2 restrictions for H, this is true in complete generality, by the way. It's nothing to do with quantum ergodicity. I'll say that in a minute. The L2 restriction is controlled by the tangential L2 restriction. Chi epsilon just denotes a certain pseudodifferential cutoff to tangential directions, right? So the key to estimating upper bounds for L2 restrictions is the tangential. Is the tangential mass. Everything else is O of 1. So in general case, again, this is no QE assumption, it's complete generality. Just from the identity I wrote down, from the Rayleigh identity, you get that the sum of squares. So in general, you don't have an asymptotic here, but you can show that this is O of 1. It's bounded, right? So in complete generality, you can show that the sum of the squares of the normal derivatives and this tempered sum of squares with this factor put in for the Dirichlet data is always O of 1. So everything, all the L2 mass is controlled by the tangential L2 mass of phi. This is O of 1, as I just said, right? So it's absorbed in here. So everything boils down to estimating tangential mass from above. Okay, so this is just what I said. So the upper bounds for the L2 restrictions are determined by the h-bar microlocal mass in arbitrary small neighborhood of the glancing set. Okay, The same is true for lower bounds. So to state the results that I want to talk about here, let me just recall the notion of a defect measure. So a defect measure just means you have a sequence of eigenfunctions, L2 normalized. The limit of the matrix elements exists, and the defect measure is defined to be just the limit of the matrix element. So if you give yourself any L2 bounded sequence of eigenfunctions, you have a subsequence. It's just a compactness diagonalization argument. The matrix elements of the subsequence will tend to some integral of against some measure d mu. D mu is some radon measure. So in the QE case that I talked about, this defect measure is just Liouville measure. It's a volume measure on the cosphere of M. The restricted defect measure, if I have a hypersurface, is just the restriction of this measure to the hypersurface. Okay, so it's just if you have any sequence of if you have bounded sequence of eigenfunctions, you have a subsequence such that the matrix elements, the limit of the matrix elements, is given by integration against some measure, and that measure is called the defect measure of that subsequence. In the quantum ergodic case, this defect measure is just volume measure. Okay, so these are just general. In this case, the defect, if you take this example of the spherical harmonic, this example here, you compute the defect measure. It's a delta mass along the geodesic. So defect measures can be singular or they can be. Huh?
So for most of them, it will be zero.
Is a delta mass.
No, in this case.
In this case, but here it's you know, you can have all kinds of measures. So in the QE case, it's equidistributed. Okay.
What he's saying is that the space of measures is we start on factor. You can always put out subsequence.
Yeah, it's a diagonalization art. Yeah.
So if you have a sequence for which limit exists, that's that, and nothing more than this.
Yeah. Okay, so I want to link this to the billiard map here, just to sort of remember the problem we're faced with now is trying to separate out the Neumann data and the Dirichlet data, right? If we can compare the two, then we have a good chance of proving the kind of restriction bounds that I'm talking about. So the key point here, and whoops, is that so suppose I have such a hypersurface inside some domain. Okay, it doesn't matter. And I have some Green's, local Green's operator, so it satisfies, it's a Green's operator for the Laplacian, the ambient Laplacian. So then I have a jumps formula along H. So if I look at the, UH will be the, UH, so if I put a super H, that means I restrict the eigenfunction to H. If I write a nu here, that means I take the Neumann data and I restrict it to H. So then I can find these integral operators as single and double layer potentials acting on H, such that I have a jumps equation along H. So this a priori relates the Neumann data. Huh? No, it's a Green's function for the, let's think about a planar domain, okay? You have a Green's function in R2, okay?
Yeah, G omega I understood what it is. It's just indeed some kind of partial Green operator, so it's not everywhere, but on omega.
Yeah, so you can talk about the restricted operators along H, and that gives you an integral equation along H. These are integral operators, okay, that relate the restricted Dirichlet data to the restricted Neumann data. I want to relate the two, so this is a relationship, okay? So the question is, can I invert either side of this integral equation to relate?
Just a second. What is U? H nu?
It's just
It's
it's just so it's notation because I'm going to be using this so often. So either you take the eigenfunction and you restrict to H. This just means you take the normalized normal derivative and you restrict to H. These objects appear so much that I have notation for them. Okay.
Okay, so phi H is the eigenfunction.
Phi H is the eigenfunction. You take the normal derivative of the eigenfunction, you restrict.
And
Okay.
the claim is that there is an
I should call it phi
operator
H or something.
from C infinity on H to C infinity on H. There are a couple of operators that
Yeah.
connect them. Okay, good.
Yeah. Okay, so the question is, can we invert this equation? And it's tempting to try and do this, right? So we tried. I mean, a naive thing would be to come up with situations where, for example, n of h is, where you can do a Neumann series invert.
Which one do you want to observe?
They're identical. Actually, the problem is that both sides are equal difficulty, so it doesn't actually. Yeah. I mean, ideally, you want to write. If I want Dirichlet, then I want to write I want to relate the Neumann data to the Dirichlet data. So I want to show. Yeah. The problem is, it's very hard to do this. So, in fact, we haven't been able to do this in any setting. So, instead, what we did was, with my former student, we considered the problem of complexifying this integral equation, right? So, what you do is you assume now h is real analytic. So far, h was anything smooth. Now you assume h is real analytic, and you try and complexify this integral equation. It's essentially what Zeldich and I did along the boundary, okay? But now it's for any curve, right? And you try and invert the complexified equation to relate the complexified Neumann data and the complexified Dirichlet data. So I may just say that these operators are quite complicated. This is the reason why you can't invert them directly. It's very hard. But there's a certain range where if you look at the Schwarz kernels of these operators and you have points along the Schwarz kernel that are separated far enough along h, so if here's your h, okay, and if q and q prime are separated far enough, then you have an asymptotic formula for what these operators look like, and they have this sort of standard WKB type formula. So you have an oscillation term, and then you have this sort of amplitude that has an asymptotic formula. And the singularities of the wavefront sets are contained in the billiard relation. So the billiard relation that I started with determines these operators, determines the singular structure of these operators. So it's very.
What exactly is W?
I forget it.
Okay.
No, it's just the singular part of the operator. It's where it's not negligible. Okay.
You have to start reading all that.
No, forget it. I just wanted to link. It's just where the operators. It's just where the operators localize in H. So away from these sets, away from the billiard mapping. If you cut off these operators away from the billiard mapping, they're negligible in H. Okay.
I think
So
it should be emphasized there that you can't prove any of these things. Well, you should never say you can't prove any, but it has never been proved using things like heat equation instead of propagation of singularities, which
Yeah.
the main tool is using. All these sharp results that you're seeing are based on micro-local analysis, of which this is the main tool.
So, but my main point here is I want to complexify this integral equation, then try and invert it. Okay. So. And that's what I said. It's unfortunately, if you don't complexify, we've tried this. It's tantalizing, but we've not be able to do this. So the idea is we complexify these things. You take h now to be, let's say, a curve, okay? So we go back to my original problem, and we have this integral equation, but now we want to complexify the integral equation. And so using this idea, I'll say a little bit about this in a minute. But with my former student, we show that under appropriate curvature assumptions on h is now real analytic curve. I'm going to assume that h is positively curved. And okay, so there's some other defect measure assumption which will be satisfied in the QE case. But what we can show is that for such cases, which I'll explain in a minute, you can relate the Neumann data to the Dirichlet data. Namely, you can show that the Neumann data is exponentially controlled, but is controlled by an exponential times the Dirichlet data. So now if you go back to the Rayleigh formula that I wrote, right, that had the sum of squares of the normal data and the Dirichlet data, that will automatically tell you that the Dirichlet data will have to have an exponential lower bound, right?
So U is the same as phi, or? No, U is,
Yeah, sorry. I went between u and phi. Whenever you see u and phi, it's the same thing.
So let me understand what you're trying to do. You're trying to give a lower bound for the L2 restriction, say, on a curve, let's say in dimension 2, you
Well-
have equidistribution on level space, you have a lower bound, which is that correct?
No. I'm going to have to put some. I'm going to have to put some assumptions on the defect measure. So there has to be some sort of equidistribution assumption. Not quite equidistribution, but the.
Yeah, but right now what we achieved is that we have an exponential low bound and we have a constant low bound.
Yeah, you have exactly, which is what you.
Trying to get a-
So this is the thing. The problem I started with is where I want to wind up. So if I have this, then I have what I want. So let me state the theorem. Maybe I won't state this way. Let me state this case. Okay. So this is the case that.
You certainly have to put a condition on H, otherwise you would be proving that
Yeah.
sufficiently large eigenvalues do not
Stri-
have their nodal domain contained in H.
Yeah, exactly. Strictly convex. Okay? So here's the theorem. So let's take omega. Take the stadium. Okay, that's the problem I really was interested in to begin with. Okay? So take the Bonamovich stadium. Okay? And take a strictly convex real analytic curve. Okay, no, don't draw very well. Okay, inside. And I come back to exactly the same problem that I started with. I want an upper bound on nodal intersections. The nodal sets you saw in this picture, the spaghetti-like thing, right? And so I take a sequence of eigenfunctions, okay? And I assume that this sequence is QE. I know that for most eigenfunctions, this is true. And then I ask the question, do I have an exponential lower bound? Do I have the unique continuation result that I want at the level of restrictions? And the answer is yes, provided the H is strictly convex and real analytic. By the way, the strict convexity also appears in Rudnick and Bourgain's results on tori. So
Right.
it's not necessary, but it, for the
No,
proof.
it's not done if you do a straight line.
Right, exactly.
Then it becomes a whole question. It becomes very subtle.
Yeah, very subtle. Yeah.
So what is your question?
The questions about restriction to a straight line segment in the torus. I mean, it's really the torus. It should be emphasized. The torus. If you took a generic torus with size 1 and alpha irrational, these problems are trivial. The interest that what they're doing is they're looking at the ordinary torus,
Yeah, when you have
and then you have this small multiplicity coming from the number of ways of writing numbers, the sum of 2 squared. And so that's the battle you have there. And if you ask about the restriction to a
Yeah.
straight line segment, it becomes a question about short integer solutions in short segments of the circle, which is an extremely difficult problem that many people have tried.
So the convexity and the strict
translation in both directions.
Yes.
Okay,
I claim that people have, I don't know that I can reproduce the books, but
I will ask you.
I mean, for the stadium, I think the following is obviously this is false, right? If you take this geodesic, it's false because it's a flip. It's a flip it, right? If you take a generic geodesic like that, it's probably true, but our proof doesn't work, right? So we have no way of.
I'm confused about one thing. I thought that if you're assuming your sequence of eigenfunctions equidistributed with respect to legal measure, and you have your condition on H, whatever, I thought that you already proved the lower bound, which is after you do this integration by parts, that's what I call it, you get this boundary equidistribution. And on the boundary, you have to cut off in the tangential direction. So you can't get an upper bound, but I thought you can get a lower bound.
Yeah, you can get you can get a little bit better than that. Well, you can get better than exponential. You can get some polynomial that goes to
Not
zero.
a uniform lower bound.
Sorry? No, you get some you can get, if you really, I was only interested in nodal intersections, but you can get something like this.
I'm talking about L2 restriction.
I know,
Yeah.
right? You can get a lower bound that's something like this. I think h to the 3/2 or something like that, if you really work it out. So it goes to 0, but it's a polynomial rate. You can actually do that, right? There are polynomial powers floating around in the, okay? Okay?
Anyway, exponential.
But that's certainly true, yeah. That's all we need, so.
Yeah, for the intersection.
Yeah, so you can improve this to some polynomial rate that goes to 0, but okay. So So this applies to QE sequences of eigenfunctions, at least for full density for the Bohnemovitz stadium, and for other ergodic billiards. So for example, for generic, think triangle billiards, and there are all kinds of polygonal billiards, large families that are known to be ergodic. You can take a cardioid, half a cardioid, etc. So let me give a rough sketch of the proof. I don't have much time. So the idea is the same as we started with. We take H and we complexify it. So this is a little epsilon strip. So here is H. I parameterize it. Let's say it's periodic, 2 pi or something. Here's H, and I take an epsilon strip. Okay? And I call this H epsilon C or something. Okay? So it's just a little complex strip, and I holomorphically continue everything. So I start with a potential layer formula. You can write the jumps equation along H. Since I now have an actual boundary in this theorem, I might as well just do potential theory relative to the actual boundary. It's the same thing, okay? So I write down the potential layer equation relative to the boundary. So the phi and u are interchangeable in this talk. I'm sorry about that. I tried to. So phi h sub h means that you take the eigenfunction, you're restricted to h. Phi h partial omega means you take the eigenfunction, you're restricted to the boundary. N is a double layer potential. It's the normal derivative of Green's function. Okay? So then you just have the potential layer equation. I'm assuming Neumann boundary condition, so there's only one. Huh?
What is omega?
It's the stadium, okay?
Okay, so omega is the whole number.
Omega is the whole stadium, okay? And H is a strictly convex analytic curve in the stadium. So then I can use the actual boundary of the stadium and do potential.
There's the data of H.
Yeah. So I just write it like this, okay? So now I holomorphically continue this integral equation. You can do this with jumps equation. It's the same thing, okay? Whether you want to do jumps equation or whether you want to do integral equations using the boundary. It's easier somewhat to use the boundary here. So then I holomorphically continue the whole thing, okay? And so this is, so the main technical part, which I don't want to get into it, is to say that I can relate, there's a certain weighted L2 mass. So you take the holomorphic, you take the eigenfunctions, you holomorphically continue them, you compute a weighted L2 mass. There's a certain weight here, so that this weighted L2 mass is actually controlled from below by a matrix element of boundary eigenfunction, the boundary restriction of the eigenfunction.
So the integral is now over the view.
It's over this strip. Okay, so I holomorphically continue the restricted eigenfunction, and there's some weight. That rho is a weight function. And I can control that weighted mass from below by a matrix element along the boundary. Okay?
What's P of H?
Sorry?
P of H, what is the
E of it.
P of H?
It's this operator.
Sorry.
I'm basically rewriting this as a T star T, as a composition of an operator and its adjoint. And the point is that, okay, for certain pieces of the Grauer tube, this operator actually behaves like it is a pseudodifferential operator. And so the point is that these matrix elements, now I have my QER theorem. I can apply it, and I can actually compute that for quantum ergodic sequences in the interior, the boundary values are also equidistributed. So there's basically a volume. And if you compute what this is, it's just some positive number. You can, there's a computation here, but you can see that for this P that you get a positive number. So it follows that, in particular, this is just some integral over some strip in the Grauer tube. So it's some subset of the Grauer tube, okay? It's here. So there's some cutoff to this strip. So the L2 mass over the whole Grauer tube is bigger than or equal to the L2 mass over some strip. And in this strip, I can write this as a matrix element of a pseudodifferential operator along the boundary. And that I can compute as some positive constant. So I've got a weighted L2 mass being greater than or equal to a constant. It's obvious that this is good. And in fact, you can get some polynomial power here out of this as well.
What are we trying to show? We are trying to show that the integral over H is large.
Yeah. So think of it this way. You can't have, if the L2 restriction along H were sub-exponential, then you could do like just a crude 3 lines lemma to argue that the holomorphic, it would be nonsense, right? You can't. But you can do more. You can get a polynomial lower bound from this. But you can't do that. Okay, so
You should get an upper bound for the
no, because this is only for a piece. I can only control the weighted L2 mass over a piece. There are other pieces of this Gara tube where I have no idea how
The
to.
upper bound is simply false. It's not.
No,
because of
but I
that
mean,
kind
if you
of-
want the C line level, you should have an upper bound on the line that is away from the real line, right?
Oh, I thought you were talking about it.
No, I'm talking about the finals.
Of course.
Eigenfunctions.
So you have to control.
Eigenfunctions do. They blow up exponentially. They blow up exponentially as you go into the complex. So the point is that they blow up exponentially, so you have an a priori rate. And if they're sub-exponential here, they're going to stay sub-exponential when you go up, which would be nonsense, right?
So you have an upper bound.
Yeah. There's an exponential blow up from
Yeah,
the.
that's what I'm saying.
Yeah.
Yeah.
Yeah. So that's the point, is that this weight compensates for the exponential blow up of the eigenfunctions.
I see.
Okay. So this proves that for example, for the stadium, so then you go back to this theorem, then for the stadium, which is this example here, you take a strictly convex curve, you have an O of lambda bound for all quantum ergodic eigenfunctions of a stadium. Okay, so then that brings me to the end here. So if you just take an open set of the ambient manifold, then this is quantitative unique continuation. So that's known. So the main question here, one of the main questions is there an analogous statement for eigenfunction restrictions in arbitrary hypersurfaces, or goodness in our terminology? So the answer is no, because you have these fixed point sets of isometries for which the odd eigenfunction is 0. But, oops. What's going on? It's not working. Oops, no, that's the end, I guess. Okay, sorry. Yeah, so the answer is no, but so the more precise question is, suppose you have a hypersurface with strictly positive sectional curvature, so like that in any dimension, really. And suppose you have ergodic geodesic flow. Do you have goodness, right? So that I believe, but I can't prove yet. So the only examples where I can actually prove it are these ones, like the stadium. So the most recent thing, so we have some work with Zeldich that we're writing up, where we ask sort of generically what kind of bounds can you get on restrictions. So we're willing to throw away density 0 subsets here, okay? But we ask the following question. So suppose that H satisfies microlocal asymmetry. So this is no perfect focusing, okay? And also satisfies what we call the charge flow out assumption. So basically, this is like a non-trapping kind of assumption, okay? So if you if you take your H and you take any point and with covector here and you go out for infinite time, you pick up everything in the Gaussian bundle. So for example, if you have a planar domain, right, then every geodesic intersects the boundary. So if your H is the boundary, that's certainly satisfied. So this is the sort of non-trapping condition. I mean, you could have situations where things are trapped in the inside. So it's a non-trapping situation. So every geodesic everywhere else comes and hits the hypersurface at some point. Then we get a very good lower bound, again, up to density 0. But there's no dynamical assumption other than this condition here. And in fact, I think we can also prove an upper bound that's consistent with this under just the microlocal asymmetry condition. So it's a sort of a generic result up to density 0, but with very little dynamics involved. So I stop there, I think.